Okay, so as promised, we continue by discussing the solution of diffusion equations, which is known as rate equations or rate theory or reaction rate theory. Um, and the word reaction here means the reactions between defects, not the regular chemical reactions or nuclear reactions for that matter. And in many ways, one can say that solution of diffusion equation is the oldest theoretical approach to understanding radiation effects. It can, in a sense, diffusion equations have been solved generally since the 1800s. For defects, it started to be used in the 1950s, 1960s, using computers, which allowed to model more complicated case systems. So the point with rate equations is that you don't deal with individual defects as objects, but deal with defect concentrations. This allows it to simulate the large-scale average defect concentrations, reactions with sinks, and so on. So even though one doesn't really deal with individual defects, as we shall see, it's perfectly possible to deal with individual defect types. For instance, describe interstitials and diinterstitials and interstitials of vacancies separately from each other with separate concentration. And here on this plot is one of the early results by current standards. One could do this much better, but it's still relevant as a way of getting an idea and as a model model results. So this shows temperature on an Arrhenius scale going from the melting temperature lower, and this was simulating simple interstitials of vacancies without any defect clustering, and what's the probability of they being annihilated at sinks. And the different curves here are different sink concentrations. So 10 to the minus 3 is a much higher concentration of sinks than 10 to the minus 4 and so on. The minus 3 is 1 in 1,000 sinks per atom and so on. And what this study showed by this rate equation modeling is that there was a relatively wide range of temperatures where all point defects could be annihilated at the sinks. Of course, if one would include defect clustering, the picture would be more complicated because some of the defects could first cluster with each other and so on. But this is something which modern rate theory modeling can include. So to give you a flavor of how rate equations work, in principle, it's a matter of solving partial differential equations. So one has for each defect species A, one has a concentration which can be a function of space. Typically, it's a function of the depth coordinate only, but in principle, it can be done fully in 3 dimensions. And then it's also a function of time, and the aim is to solve the time dependence of the defect evolution of the defect concentration. And the simplest term here is the diffusion of this species. So this can, for instance, be in a vacancy migration or interstitial migration, and typically is described with the Arrhenius factor as mentioned. So these first 2 terms is the basic diffusion equation for a single species. But then to be able to deal with more species, one can add the interaction between species, and this is the 3rd term here. So this is the trapping and trapping equation, which means that you have concentrations of 2 different species, Ca and Cb. Obviously, the probability of trapping will be related to the product of these concentrations. Then you have both diffusion terms and the radius, which is known as the radius of trapping, which can be obtained, for instance, from molecular dynamics or density functional theory simulations. Then the detrapping, which was mentioned, can also be included. So in this case, one has a species B which can detrap from A, and that has an own Arrhenius factor of its own. And then there is, for practical purposes, it's very important to have a source term, which means that you can introduce new defects. This can be just a single term, but can also be a combination of many different terms. So this is the basic idea, but note that this here is for one defect species. Then you need to write for each defect species you are interested you have to have a similar set of differential equation, which then, due to the trapping and detrapping, may depend on all other types. So one gets a pretty or quite complicated set of coupled differential equations. But they can be solved with numerical, iterative numerical terms means. And just as a simple example, this is a solution of the diffusion equation for deuterium implantation of tungsten. Here a source term would be the as-implanted curve, initial depth profile, and then this shows how the depth of deuterium evolves with time and for over a 1 millisecond time as a function of temperature. So at 300 kelvins, this as-implanted deuterium concentration would have broadened to something like this. 400 kelvins, even more. At 600 kelvins, a lot of the deuterium would have vanished at the surface, but some would also go much deeper into the crystal. That was a bit simplified because that at the high concentrations, diffusion actually depends on concentration. This is known as concentration-dependent diffusion, which in general is a well-known effect in diffusion studies. And this complicates the system, but it can be handled if you know the diffusion concentration dependence. You can take it into account, and one sees that one can actually have a huge difference between depending on if you model the diffusion concentration independent or dependent. And well, now I won't go into much more detail. As indicated, there is a big literature on this. I'll just give one example of what can be actually with rate theory modeling. So this here is experiments and simulations of a 30 kV implantation of deuterium into tungsten at 3 different energies, 5, 15, and 30 kV, and then measuring the deuterium concentration after the fluence. And because of these migration effects, there is migration going on. But anyway, here you saw that these rate equation simulations could match the experimental profiles essentially perfectly in this case. But achieving this is not easy. In this, it looks very simple. But this here is the number of defect reactions which went into the rate theory modeling. There is no reason to understand or know the details. I just wanted to show that there is any number of reactions you need to include. So here is hydrogen interacting with a vacancy of different size and a hydrogen one clustering with it. You see the range of sizes here was already, this first process had 30 different varieties for size, and then the list goes on and on into more and more complicated processes, and all of these have to be parameterized. And the way they are typically parameterized in this study and other studies is based on density functional theorem, classical molecular dynamics results, which can then allow parameterizing these factors and then including the defect reactions. These MD simulations can be also useful in giving the trapping radii and so on. So that was the rate theory. Another approach to simulate defect migration is with the kinetic Monte Carlo approach. And the inputs to kinetic Monte Carlo, these defect reactions, can actually be the same as in rate theory. So looking at this graph, all of this data can also be used to set up kinetic Monte Carlo model for the physically the same process, but then the evolution is followed in a very different manner. So the point is in kinetic Monte Carlo is that you model each defect explicitly as an object. This is known as object kinetic Monte Carlo. And after that, you can use this kinetic Monte Carlo algorithm to simulate the time evolution of the system. Here one might mention that this kinetic Monte Carlo method is sort of funny in the sense that it was invented independently of each other at least 3 times. And it has also been called different names. It has been called dynamic Monte Carlo, the residence time algorithm, Borz-Carlos-Leibovich algorithm, these were the people who developed the residence time algorithm. And then there is the n-fold way and the Gillespie algorithm. And if you're interested in detail, you can check the Wikipedia page, which has references to the original names and papers. But the basic idea of the kinetic Monte Carlo using the residence time algorithm is here. First, you form a list of all possible transitions in the system, and these transitions can, for instance, be defect jumps. You can have one defect jumping to another place with a known rate, and this is one of the inputs to this. Then if you have this way defect number 1, then for defect number 2, even if the rate is the same, you have to have a different transitions because each defect is distinguished from each other. Then after you have all the rates, which can happen, you calculate the cumulative function of them. This is simple numerical mathematics, nothing special here. Then this is the crucial part of the resonance time algorithm. You get a random number using standard random number generation techniques. Then you carry out the event, which lies between Ri-1 and Ri in this cumulative function. So a cumulative function is, of course, a monotonously raising function. So this means that you generate a random number which then picks one event here, which is where you have in this sum here. Then you move the time forward. Note here that this is a minus sign because you take a logarithm or a random number within 0 and 1. This logarithm is a negative number, so that's why you need a minus sign to take it forward in time. And here we divide with Rn, where Rn is the sum of all events in the system. Then after you carried out this single jump event or single reaction or whatever it is, you find out all the possible changes in these and repeat. Recombination is usually done as a non-activated process. So if a defect after the jump, if an interstitial is very close to the vacancy, then in this stage, you would make the interstitial react with the vacancy, and which would mean that both defects recombine with each other, then remove this interstitial and this vacancy from the list, and then go on with the simulation without those. So the great thing about the KMC algorithm that for so-called Poisson processes, that is processes which occur independent of each other at constant rates, this is actually exactly correct. It's random because it has these random numbers in it, so it's stochastic, but it's still exact. If you're interested in mathematical derivation of this, you can check this very nice review article of the method. So you may wonder about this stochastic but exact, but this does make sense that this reality is also stochastic. In reality, the jumps also occur on a random quantum level atom vibration processes, so in reality it's also stochastic, but still the average number you get will be exactly correct. And it's very typically used exactly to simulate atom diffusions. The rates are simply the atom jumps. But you note that these rates and reactions have to be input to them, and the algorithm cannot predict them. So you have to know which reactions are occur, at which rates they occur, which capture rate are there, and so on and so on. But as said, if the basic approach to get them is the same as for rate equation, you can obtain them from DFT or MD simulation, ideally from experiments, but very rarely are the defect reaction processes known experimentally well enough to be used in a more complex system. The migration of a single atom in a pure element is typically known experimentally, but that's about it. Then, of course, you can use, if you don't know all the parameters, you can try using free parameters, but that's something which is, of course, dangerous, because if you have many free parameters, then it's very unlikely that you can deduce any physically reasonable conclusions. I also like to mention that there are many varieties of kinetic Monte Carlo. What I was describing for defects is known as object kinetic Monte Carlo. Each defect is an object, impurity is also an object, and you ignoring the lattice atoms. It's also possible to simulate every atom in a lattice, at least if you are crystal structure explicitly, and then this is known as atomic KMC. And then there are other varieties of KMC, which are essentially ways to speed up object KMC, going from one reaction to the next. So as reaction KMC and first passage KMC. Out of these, this newer first passage KMC is considered to be mathematically more rigorous and more reliable nowadays. So basically what these methods try to do is, since a single interstitial jump is not very interesting, and if it's far from any defect, it won't do anything really interesting except jump around randomly. They try to speed up their approach by jumping, grouping many interstitial jumps as long as it's far from other defects into getting the interstitial or whatever close to another atom and do a reaction there. Then there are also many varieties of so-called adaptive KMC, where you have atoms in the system and try to detect possible barriers on the fly without it having to pre-tabulate them, and then you get rid of this, that you have to know the reactions in advance. On the other hand, to do this, you essentially have to run a molecular dynamics or molecular dynamics-like simulation within the KMC to obtain these events. And for this object KMC for defect, as I already indicated, the basic object is a defect or impurity. Non-defect lattice atoms are not described at all. This is what makes it much more efficient than molecular dynamics, because you may have millions of perfect atoms, which molecular dynamics would need to handle all of them, but object KMC can just ignore them and only treat the defects which are of interest. The process is a diffusive jump occurring at an arrhenius rate, but then you have these reactions like the monovacancy clustering to a divacancy and so on. And as indicated already, that defect reactions are typically dealt with a simple recombination radius. If two species are closer than the recombination radius, they instantly recombine to form a good defect complex. And now, without additional detail, there are, of course, courses which describe KMC separately and give a lot of details and review articles. I'll just give a couple of simple examples. The first one is really extremely simple. This is modeling helium mobility and bubble formation in tungsten. This simulation was done some 15 years ago, and it's now we know it's not fully correct. But the qualitative picture it gives is right. So what's modeled here is a single mobile species, helium atoms in tungsten, and this was put at an experimental fashion, but then it was assumed that when two helium atoms are close to each other, they recombine and become an immobile complex. And all of these helium clusters are assumed to be immobile bubbles which grow in tungsten. And this is actually quite realistic. Later simulations show that when you have two helium atoms next to each other in tungsten, they do recombine and form a cluster which is almost immobile. And when the cluster goes to about 5 or 6 heliums, it's completely immobile, at least at room temperature. What you see here is that first the helium moved freely, but after a while, due to this recombination, they start growing bubbles, and these bubbles grow in size close to the surface. And what you notice is that after a while, nothing happens deeper in. The helium is input in a depth profile close to the surface, and after you form these bubbles, all helium very quickly becomes trapped in the bubbles, and these things just grow. This is a three-dimensional simulation, of course. That's why it looks like the bubbles are on top of each other, which they are not. But later on, experiments show that this process is actually quite realistic, that this happens indeed more or less like this, that after some helium concentration, the helium forms bubbles, which then traps all further helium. Notice here the time scale, that in this simulation one could actually simulate 20 seconds of real time, which whereas in molecular dynamics it's very, very difficult to come to exceeding to nanosecond time scales. Well, this was, as I said, a simple example. Now I'll give a somewhat more interesting and complicated example of defect mobility in silicon with recombination and cluster reactions. This is also a simplified model. There is no detrapping or cluster mobility, but this model would still, let's say, be in the right ballpark compared to more modern models. We'll give an example of more modern model for silicon migration later in this. And here are the parameters which used. So these are the interstitial vacancy mobility in silicon, and this in Arrhenius factor. So these can be used at any temperature. Note here that here the vacancy is more mobile than the interstitial, which in silicon actually indeed seems to be the case at least at high temperature. And in this case, the simulation set up by putting defects in, but at slightly different depths because of ballistic effects, because of atom kicking the atoms deeper in. Its interstitials are expected to be somewhat closer to the surface than vacancies. And in this case, there were two depth profiles with vacancies closer to the surface than interstitials, but the difference was only 5 angstroms. And then running a KMC simulation, one can see what happens. So these plots show the functional time. Note how here we go are many orders of magnitudes of time from 10 to the 6 femtoseconds. So this is 1 nanosecond, and to 10 to the 13 femtoseconds. So this is already 10 milliseconds. And follow the defect concentrations. So initially there were only interstitials of vacancies. Some of them happened to be very close to each other, so they recombine extremely fast. But for a while, you have mainly interstitials and vacancies, and then they start recombining. But here you can follow what happens with the system. So the green curve is the number of recombined defect pairs, which in this model were then became immobile, but then they can also vanish at the surface. So at first, the more mobile vacancies started vanishing at the surface, and not so much happened with the interstitials, but after a while, what happens is that almost all of the vacancies have either recombined with interstitials or vanished at the surface. So all three interstitials vacancies are gone, and then after that, the interstitials start to dominate the behavior. And then what happens is that the interstitials start on longer timescales start become mobile and vanish at the surface. And eventually in this model, you reach a steady state where all defects either have vanished at the surface or become immobile defect clusters. And these points here illustrate what it looks like from the simulation. And note that the number of defects was relatively small, so it was only about 170 defects in this small simulation cell. So in this case, we had a 2 nanometer cell in the y direction, 30 nanometer in the depth direction, and the surface is to the left. And also in this case, we had a simplified z coordinate, so we had only 1 angstrom depth in the z coordinate. So you see that initially the purple ones are interstitials. Initially the interstitials don't do almost at all because the vacancies move much faster. But then after a while, almost all vacancies are gone or are gone to the bulk, and changing the scale, one sees what you have. You have these interstitials close to the surface, but then running this for a very long time, the vacancies find their way back to the interstitials and recombine. And then eventually the interstitials also become mobile and go to the surface, and in the end one has only a very few slowly moving interstitials left. And then once this model is set up, one can test how this works at different temperatures. So at 1300 Kelvin, one has a similar but not quite the same picture, because here the interstitials are more mobile because the temperature is higher. And then the difference in activation energies is less. And then we have a process where things happen more on a roughly similar timescale for interstitials or vacancies. But also here, the way in the end, the interstitials are what's left. And by the way, these temperatures, 1000, 1300 Kelvin, are quite relevant to the processing of silicon in the semiconductor industry. This is not an abstract model that is studied just. So this was to give a flavor of what can go on in kinetic Monte Carlo. And in the final set of this section 8 lecture notes, we give some more specific examples of long time scale and high dose radiation processes.